Good morning, everyone. I'm Shikai from Northwestern University. Today, I'm happy to share with you some of my recent work on multi-scale nanostructure enable spatially defined graphene properties. As we know, one of the most exciting applications of 2D materials is for ultra-thin electronic devices, like monolayer electronic devices. Even in smaller layers, it still have the same component as what we have for the bulk electronic devices. We still have conductors, semiconductors, and insulates. So in order to achieve these small layer devices, people start to assemble different 2D materials side by side from these lateral heterostructures. For example, we can use graphene as conductors, hexagonal nitride as insulators, and transition metal dicotinite as semiconductors. However, because of the different lattice constants of different 2D materials, when we form these lateral heterostructures, we can introduce dislocation defects at the boundaries, and we can also introduce the strain in the boundaries. The dislocation and the strains will decrease performance of the electron devices by introducing mechanical instabilities and actual scatterings, electron scatterings at the boundaries. So in order to avoid this lattice mismatch, we can have single materials with spatially defined electronic properties. Since we have only single materials, so all the lattice should be same. Along these lines, we know graphene is zero bandgap semiconductors. It also can be called semi-metals. Another important properties about graphene is we can functionalize the graphene. For example, by introducing different fluorination levels in the graphene, we can modify the bandgap structure of the graphene and change the graphene from conductors to semiconductors, even to insulates. So to solve these lattice mismatch issues, we can just pattern in the graphene with spatially defined fluorination levels to make a monolayer devices. So how can we achieve that? So let's first imagine we have a flat graphene. Then all the electrons should be stay in these flat pi clouds. As we introduce the lattice deformations in the graphene, actually, we are not only bending the carbon-carbon bonds, but also introduce deformation in the electron orbitals. So by introducing the local curvatures in the graphene, as you can see here, we introduce pi sigma rehybridizations and also electrochemical potential variations in the graphene. This actually will change the reactivities of the graphene with higher local curvatures with more reactive the graphene. So in order to achieve these spatially defined fluorination levels, maybe we can first introduce the spatially defined local curvatures in the graphene, then through some reactions, then we can achieve these spatially defined fluorinations. So this means we have to have an ability to precisely control the local curvatures in the graphene. However, this is very challenging because previously the way we introduce the local curvatures in the graphene, we have to use the crumples. Crumple is because of the low weak adhesion between the graphene and the substrate surface. When we form the crumple structures, we always form the denominator features. These denominator features will make the crumple non-uniform in large scales and form the high density of cracks. All of these features is not good for the electronic applications. So in order to achieve this, what we need maybe is we have a method to introduce multi-scale nanostructures with on-demand size and also control the local curvatures. A few years ago, we found if we treat the substrates like polystyrene surface with CHF3 plasma, instead of etching the substrate surface, we start to form a rather thin fluoropolymer on the substrate surface. We call it skin layers. By further shrinking the substrates, we can form the nanowrinkles in these skin layers. Another interesting features or important applications of this method is we can precisely control the wrinkle features like the wavelengths, amplitudes by control the thickness of the skin layers through the reaction time. So this is very good for our applications. So by transfer graphene on these skin layers, then further shrink the substrates, then we can introduce the wrinkle features in the graphene on the fluorine polymers on the substrates. as you can see for some AFM results showing here. This gives a great power to design the local curvatures in the graphene. So similar as the previous method, we still can introduce crumple structures in the graphene just by transfer graphene on bell polystyrene part surface, then shrink the substrates. We can introduce crumple structures um, in the graphene, as you can see from the AFM result showing here. More importantly, we can control different wrinkle structures in the graphene, and we have a 1D wrinkles and 2D wrinkles by just changing the substrate strength directions is uniaxial directions or biaxial directions. And we can further control the wrinkle features by control the magnitude of the strain we introduced by the shrinkage of the substrates. As you can see, here we're showing some examples. When we increase the strain, the 1D wrinkle form the along the 1D directions. And as we increase the strain at a higher strain of 1D wrinkles, the wrinkles start to touch each other to form these fold structures, and the wrinkle peaks start to flatten, which means at a highly strained 1D wrinkle, we have lower local curvatures. And the 2D wrinkle is rougher than the 1D wrinkle, is at all the strain levels, and at a higher strain, it starts to form these self-similar structures. For the crumples, it's even rougher than the 2D wrinkles, and is have a higher density of high curvature size compared to 2D wrinkles and 1D wrinkles. So the local curvatures of the crumple is even higher than the 1D wrinkles and 2D wrinkles. So based on these observations, we start to design our experiments. Since we want to introduce the spatially defined local curvatures, then we can pattern different local features like wrinkles and crumples side by side in a single graphene sheet, right? So we start to use the polystyrene as a substrates. Then we use the PVP as sacrificial layers to introduce patterned skin layers on the polystyrene surface. Then we transfer the graphene, cover the polystyrene, pattern the polystyrene on the pattern the skin layer on the polystyrene. Then shrink the substrates, introduced wrinkles on the skin layers and crumples on the bare polystyrene parts. As you can see from the FM results, we can have side-by-side wrinkle features and the crumple features in the single graphene sheets. Then we use the CF4 plasma to treat the structural surface of the graphene. And because we have different local curvatures in the wrinkle region and crumple region, if our theory was correct, was right, then this wrinkle region and crumple region should have different formation levels of the same reactions. This is exactly what we saw in our experiments. But before I introduce the experiment result, I want to give a very brief introduction about the tools we use to observe the surface functionalizations. We use the Raman spectrometers to observe the wrinkle, to observe the fluorinations on the graphene surface. In the graphene spectrals, we mostly focus on 3 peaks, as you can see from here, D peak, G peak, and 2D peak. We use the peak intensity to probe the surface properties. As you can see, the intensity ratio of D peak to G peak is used to characterize the disorder level of the lattice. And then the intensity ratio of the G peak to 2D peak is very sensitive to the surface charge density. So if we have a higher fluorination levels on the graphene surface, our ID-IG ratio and IG-I2D ratio should both increase. So back to our experiment results, as you can see before the reactions, even we introduced crumple features and wrinkle features in the single graphenes, we didn't see that much difference in the Raman mapping of ID-IG ratio and IG-I2D ratios. But after reaction treated after CF4 plasma reaction treated graphene surface, we start to see the contrast. As you can see, the graphene, so the crumpled graphene is much deep red colors than the wrinkle regions, which means crumple region have a higher fluorination levels, which means the crumple was more reactive during the reactions. This is because crumple is have a higher local curvatures than the wrinkle regions. So by doing this, we demonstrate by introduce spatially defined local curvatures, we can introduce spatially defined chemical reactivities in the graphene as well as surface functionalizations in the graphene, right? Then we further demonstrate the electronic properties can be also controlled by these methods. So before the reactions, we will measure the surface conductivity in the conductive event setups. We can say both the crumple region and the wrinkle region are very conductive, and the crumple region even more conductive than the wrinkle region because they have a better contact with the FM tip during the measurements. So the formation will reduce the surface conductivities um, of the graphene. After reactions, the wrinkle region become more conductive than the crumple region. Again, because of the crumple region have a higher surface functionalizations, formations, covers than the wrinkle region. So they have a higher further reductions of the conductivities than the wrinkle region. So this is further confirms or demonstrate that we can, by introduce spatially defined local curvatures, we can spatially define the chemical reactivities as well as further control the surface electronic properties of the graphene, which is quite amazing. We didn't stop here. We think if in order to make a more functional electronic devices, we can have a high order difference electronic properties more than just two levels. So we make a more complicated structures, like introduce these multi-scale wrinkles. As you can see, we can have a three different level of wrinkles, a scale of wrinkles, and one scale of crumples in a single graphene side by sides. Then we do the characterizations. Before the reactions, as you can see, the surface conductivity is quite same in different on different regions of the graphene. But after surface reactions, because the selective reaction happens, then we can have four different magnitude of surface conductivities in the graphene side by side. So by doing this, maybe we have the very promising method to introduce monolayer devices um, by spatially define the local curvatures and combined with chemical reactions to spatially define the electronic structures of the graphene. So in summary, we introduce a simple and scalable method to introduce multi-scale graphene wrinkles and crumples to introduce different local curvatures, and combined with surface reactions, we can spatially define the chemical function compositions of the graphene. And further, we can use this combine the local curvature control and the reactions to spatially define the electronic properties of the graphene. In the end, I want to thank my advisor, my group member, and my collaborators. And also I want to acknowledge my funding supports and my research facilities. In the end, also I want to thanks for your attentions. Please feel free to ask any questions or give any suggestions and comments. Thank you for your attention.